Okay. So now after that, we have the topic nuclear energy levels. Let's have a look over that also. The topic is nuclear energy levels. Okay. So when the alpha particle is ejected from the nucleus, okay, it is exploded like an explosion where small butter flies apart from the big one. Okay, let me show you in the diagram also this part. So we have analogy over it. Check. Okay. So when a alpha particle is released from the nucleus, what happens is it becomes like an explosion and it releases small particles from the bigger one. Okay. And the amount of energy released during these explosions is calculated as the kinetic energy. Okay. So now, applying the principle of conservation of or momentum, we can say P before is equal to P after. Okay. Let's have a look. So as per this, it was at rest in the start. Then it had started to move with 100 meter per second. Done. So starting it was at rest. Then it got 100 multiply 1 minus 800 is moving with the second one. Check. Right? 800 is moving with V speed. 1 kg is moving with 100 speed. So 1 kg is moving with 100. 800 is moving with this speed. Any doubts? I had put a minus because they both are going in the opposite direction. Check.
Yes, ma'am.
Okay.
Yes, ma'am.
0.125 meter per second. So the kinetic energy of large ball is half into 800 into 0.125 square is equal to 6.25 joules. Done.
Yes, ma'am.
Kinetic energy of small ball will be half into 1 into 100 square, that is 5000 joules. Understood? So this is how you will calculate their kinetic energies. Any doubt?
So like the V will be like or like given in the question.
Yeah.
Like always, ma'am.
Sorry?
Like the V will always be given in the question.
If it is not given, then you need to find out.
Okay.
By applying the formula.
Yes.
Otherwise, most of the time they are giving this.
Yes.
Shall I give you one question? Will you try to do it?
Okay, ma'am.
Then it will be more easier for me. But just 2 minutes of the time, not more than that. Do it. Are you done, Akshita?
One second, ma'am. Is this the like like the other one, ma'am? The product minus the
Yeah.
Okay.
Are you done? Okay. Akshita will go for the next topic. You can do it afterwards also. Okay.
Yes, ma'am. I just calculated the mass. I need to do the other one. Okay, ma'am.
Okay. So beta minus dk we are calculating right now. Already we had discussed it a lot. Okay. So
Yes,
basically, suppose here I have a neutron. It gets collided with a proton. It will release beta minus particle, and so it will release anti-neutrino. So in beta plus, neutrino is released like this. Beta minus anti-neutrino is released like this. Okay. Let me show you one example. Carbon 14,6 is going under nitrogen 14,7. So 7 minus 1 will be 6. You just have to balance the products with the reactants. So it will be beta minus 0, obviously. As it is beta minus, so it will be anti-neutrino. Done?
Yes, ma'am.
So the graph that is related to this particular thing can be shown as something like this. Okay, so this is the kinetic energy. This is at the highest peak. That is 0.2 MeV kinetic energy it bears. Okay. Now
Yes,
after
ma'am.
this, we are having beta plus decay. Already I had explained you this term. Okay. In many a times, but let me give you one example for this also. Na2211 is there. It undergoes 2210 Ne. Obviously, neutrino plus 1 0. Okay, so beta plus 1 0 and plus 1 neutrino. Understood? So this is how
Yes.
it will be done. That means when one proton collides with one neutron, it will release positron, that is beta plus. Also, it will release one neutrino. You
Yes,
have
ma'am.
to take care all the things when we are doing study nuclear physics. There is no electron participating in this. Only we are talking about nucleus and nucleons. Understood?
Yes, ma'am.
Any doubts?
No, no.
Kindly draw the graph for this now, if you understood. For the
Yes,
kinetic energy graph.
yes, ma'am. So it's like the third one,
Hmm.
or like the opposite. If it is like this, then it will be like, mm,
Okay, fine. So now, let me tell you how neutron number and proton numbers actually give the line of stability, how much they are stable. Okay.
yes, ma'am.
Okay, check here. So neutron numbers as the increasing, proton numbers are also increasing, but till 20 they are at stable nature. After this, it becomes deviated. How? The neutron number increases, sorry, the proton and the neutron numbers, same line is over here. Can you see this? And this is
Yes,
the line of stability is there. Okay, for stability, their number of neutron and proton changes and it gets deviated after that and reaches 120 or for higher elements. So for stability, number of neutrons actually increased in comparison to number of protons so that they can balance the mass of the atom. Understood? Whereas standardly, it should go like this. Understood? The dotted line. Any doubts?
no, ma'am.
Okay. Now, let's talk about the gamma radiation also. So, in gamma radiation, there is no change in the atomic number and the mass number. So it is unstable. With the star, I am showing that. So it will become stable by releasing some energy which is calculated as gamma energy. Done?
Yes, ma'am.
But here you will find no difference in the mass number and atomic number. So now after this, we are having decay concept to be studied. So basically, your radioactive decay is a random process. Okay. Also, it is spontaneous in nature. Okay. So the rate of decay gets unaffected by the external factors. That is, you can say temperature, etc. Okay. And the quantum physics is only applied to small scale systems like your atom's nucleus. However, it might help us to understand some of the concepts. Okay. That is, if suppose I consider and I observe more directly like bursting bubbles. Fine. Then if you blow the bubble with soapy water, it is very difficult to predict when is the exact time it is going to pop up. Isn't it?
Yes,
So
ma'am.
it might last for a very few seconds. It might last for a several minutes. So we can say that the popping of the bubble is fairly random. Correct?
Yes, ma'am.
So if we have lot of bubbles, then lot of them will pop up at one time, lot of them will pop up at another time. Like that it will happen. Okay. So the number of popping of each second is directly proportional to the number of bubbles. Are you getting?
Yes, ma'am.
The number of popping which is occurring each second is directly proportional to okay. So I'm giving you one question. Just solve this. Or you can take the screenshots. Check. Okay. Please do it. Be quick.
Yes. Mm.
Akshita, are you done?
No, no. 1 second.
Kindly be quick.
Negative, ma'am.
Sorry.
This like the binding energy is negative for not the binding
Hmm.
energy, the mass So that means the energy will be like there will be more energy required to like do the beta minus decay, so the decay won't happen.
Okay, do the next one. Okay, please do it when you are free. Okay, the chart is already shared with you, the board. So let's do the next topic, that is decay constant. That is nothing but lambda. Okay, so let me show you a picture over here. Check. So in this, exponentially with time, they are integrating. Okay, they are decaying. What is the formula for this? So this is known as the exponential for a decay, and the formula is n equals to n naught e की power minus lambda t. Okay, where n is the number of atoms after time t. Lambda is decay constant. N naught is number of nuclei present at the start. Done? Understood?
Yes, ma'am.
So here is the graph. You can see that exponentially they are degrading. It is a more steep graph in comparison to red, and blue is the least steep graph. Correct?
Yes, ma'am.
Okay. So that means what? The half-life of green is very high in comparison to red, because you have to collect the total time. In total time, in half time, how much it got degraded, that will be half life of that particular element. Okay.
Yes, ma'am.
Understood? Done.
Yes, ma'am.
So with the steepness of the graph, you can identify that how much half-life it had got. Understood?
Yes, ma'am.
Okay. So basically, let me give you a particular data of decay curve. So check here. Check. Original number of nuclei are 100. In 6 seconds, they get decayed completely. Okay. So here, 100 nuclei, number of nuclei are getting decayed in 6 seconds. Now, after 1 second, you can see half of them, that is 50 nuclei had already left. So that means half-life is how much? 50.
Yes,
Correct?
ma'am. Yes, ma'am.
Understood? Second
Yes.
half-life will be at 25. Third half-life will be at 12 or 13. Understood how we have to find out? So
Yes,
there is
ma'am.
no formula, but yeah, you can actually take out the half and half of the number of nuclei after every half time of the decay process. Done?
Yes, ma'am.
Okay. So now each time a nucleus decay, a radioactive particle is emitted. Okay. So the energy is released obviously. So the rate of decay is the same as the rate of emission. So this is called activity
Yes, ma'am.
of the sample, and it is measured as A equals to lambda times N. So this is the equation. Okay. Now as we are aware, N equals to N naught e power minus lambda t. So A can also be written as lambda times E N naught e power minus lambda t, which will be nothing but A naught. Correct?
Yes, ma'am.
E to the power minus lambda t. So this is the third equation. Any doubts?
No, ma'am. I'm just
Sure.
copying one second.
Acha, acha. Do it.
Yes, ma'am. Ma'am, it's complete.
Are you done?
Yes,
So now after this, we are having count rate. Okay. So let's focus upon the next topic, and that is count rate. So what is count rate? Check. Count rate is basically C equals to C naught e power minus lambda t. Okay. So higher the activity of the source, the higher will be the count rate a detector will detect for the ionizing particles. Understood?
yes, ma'am.
Write down.
Hello, ma'am.
Hello, Akshita. Am I audible?
Yes, ma'am.
Sorry, that was a technical glitch. Fine.
Yes.
Let's continue. Visible to you?
No, no, not yet. I think it's loading. Yeah, now I can see it.
Okay. Start writing.
Yes. I can see.
Okay. So for the count rate, the formula is C equals to C naught. So C is the count which is happened after time t. C naught the initial count when we had started the activity. Lambda is the wavelength of that. T is the time taken. This is exponential. Anything else?
No, ma'am.
Write it down.
Yes, ma'am.
Now after this, we are having background radiation. So basically, what is a background radiation? Let's talk about that part also. So radioactivity is a natural phenomena. You have understood, right? So there
Yes.
are radioactive isotopes that are found in the rocks, building materials, and even in our bodies. Okay. Now this all add up to give a background radiation alpha, beta, gamma, which is calculated by Geiger-Müller counter. Understood?
Yes, ma'am.
Okay. Now after this, some radiations that are actually going through this process, they result in some systematic error also, like the background count is also measured separately. The count rate can be corrected accordingly. Okay, then the source radiation may be something like the surrounding rock and soil. Some rocks contain radioactive materials such as uranium, thorium. They also decay over a period of time. Then the air, which may contain the radon gases, okay, which is also
Yes.
emitting the radium which is present in the rocks, they also decays by emitting the alpha particles. Done. Then some
Yes.
houses built into rock particularly rich in radium can have a very high concentration of radon gas. Correct.
Yes, ma'am.
So the people living in these houses are advised to have a very good ventilation so that they may not affect them. Understood? Now, the sun is also there, which emits a very fast moving particle that arrive at the surface of Earth. They are also known as the cosmic rays. Correct? So
Yes, ma'am.
these are the examples where you get the background radiations. Fine. Anything you would like to ask?
No, ma'am.
Okay. So now let's move for the next topic, and that is lambda and half-life. So what is the relation between the two? Relation is the same. N naught over 2 is equal to N naught e power minus lambda t. This is the relation that we have. From here, I can even write that my half is nothing but e minus lambda t, and t is obviously the half time. You have to take the half time, okay? Keep this in mind because half life we are calculating, correct? That's why this is n naught by 2. Anything you would like to ask?
No, ma'am.
Sure.
Yes, ma'am.
So as we have to convert this exponential part, so I will take ln at the other side. So ln of half is equal to minus lambda t half value. So I think I will get ln of 2 is equal to lambda t half. Correct?
Yes, ma'am.
Okay. So that means t half, if I need to find it, will be 0.693 over lambda. So half-life and wavelength. This is the relation. Understood?
Yes, ma'am.
Okay. Let's do one exemplar question for this. Question is saying protoactinium is there, which is having a half-life of 70 seconds. Sample activity is 30 BQ. Okay.
Yes, ma'am.
Okay. So here it is written, Akshita, coming back to the topic, it is written a sample has an activity of 30 BQ, calculate its activity after 10 minutes. So what is BQ? BQ is basically becquerel, okay, and it is actually the SI unit of activity, okay,
Yes, ma'am.
and also 1 becquerel means 1 decay per second, okay.
Yes, ma'am.
Done. So now it is saying 1 BQ is the activity. Let's connect all the points and we have to collect activity after 10 minutes. Done. So
Yes.
let's do it. We are aware A equals to A naught e power minus lambda t. Fine. Let's find out the lambda first for this. So lambda is 0.693 over half life. So that is 0.693 over half life is given as 70 seconds. So divided by 70, it will be 9.9 into 10 raised to minus 3 per second. Let's find out the activity after 600 seconds. So it will be 30 multiply e power minus 9.9 into 10 raised to minus 3 multiply 600. So it will be 0.08 PQ. Understood?
One second, ma'am. Yes, ma'am. Yes, ma'am.
Okay, so your homework will be you have to do the study for application of radioactive isotopes. Okay, do it at your own. What are the application of this?
Yes, ma'am.
Done. Now after this, we are having our next chapter and that is E4 fission reaction. Let's have a look over this chapter now. So in fission reaction, obviously a larger nuclei which is unstable in nature will undergo the process of fission and the daughter nuclei are released in that. Understood? This is called nuclear fission reaction. So let's have a look. What are the unstable nuclei? So here binding energy per nucleon is calculated in MEV, mega electron volt.
Yes, ma'am.
Just 1 second, Akshay.
Okay, ma'am.
Am I audible, Akshita?
Yes, ma'am.
Okay. So in nucleus, I'm saying a strong nuclear force of attraction is released. Done. Now this strong nuclear force of attraction, till the point it is acting, okay, the atom is said to be stable. Okay. So till iron, the atoms are said to be stable. After this, as you go far away, the electrons are not bounded by the nucleus by that much force of attraction, and hence due to less energy it loses its stability. Understood?
Yes.
And it undergoes fission reaction. Now this fission reaction happens in the nuclear power reactor. Okay, let's have a look over there also. So what is nuclear power? Nuclear power is obviously calculated in MeV. Energies is calculated in this. Okay. So we have some nuclear fuels. That is nothing but you can say uranium. 1534. 1, 2, 3. 1, 2, 3.
Ma'am, can I just use the washroom and come?
What?
Can I just use the washroom and come?
Yeah, sure. Go.
Hello, ma'am.
Yes, Akshita, just give me a second.
Yes, ma'am.
Fine, Akshita. So uranium is the fuel, okay, which gives out energy density of 1534 million energy density per megajoule per liter. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. And coal gives out 72.4 energy density per megajoule per liter. Okay. Now let's have a look that how does this chain reaction takes place in action. So somewhere like we have one uranium atom which collides with a neutron. Okay. And hence it changes its mass number. Check. One uranium atom 235 collides with neutron, it becomes 236. So the mass number is changed. Now, lot of energy is there inside, hence it will collide with two neutrons now, and it will become two half and half, that is called barium and krypton. Okay, with barium and krypton, again it will release, it will collide with more number of neutrons, and it will release more energies, and it will split into more two daughter nuclei. Understood?
Yes, ma'am.
Let me write it for you. So uranium 235 92 gets collided with the neutron, and it becomes 236 uranium 92, which collide again with the neutron, and it will give you barium and krypton. Okay, wait, let me. Okay, so the reaction is when one neutron gets collided with uranium 235 92, 14156 barium plus 9236 krypton will release three more neutron and energy. Now these three neutrons will collide with more uranium atoms, and this is how chain reaction is carried out. Understood?
Yes, ma'am.
Okay. After this, we have moderation. So basically, after chain reaction, we need to moderate it also. So the neutrons will only be absorbed if there is traveling with a very slow speed. Okay, otherwise they will pass straightly through the atoms and they will not collide with them. So in terms of kinetic energy, this would only be 1 electron volt, okay, which is much less than the mega electron volt. Done. So they possess, after being expelled during the fission process, okay, and to achieve a chain reaction, we need these neutrons to be absorbed so that they need to be slowed down or they can be moderated. Okay, now how is it done? It is introduced, this is done by introducing small nuclei between uranium-235. Done. And the water is sometimes used as the moderator. Understood? It contains hydrogen nuclei. So the neutron collides with the hydrogen nuclei and uranium-235 nuclei, and hence they have a similar mass to the neutrons, and they receive the energy, and the neutrons slow down in a non-elastic collision. Understood?
Yes, ma'am.
Akshita, any doubts?
No, ma'am. Hello, ma'am.
I'm here.
Yes, ma'am.
Check. So this is how the moderator nuclei participate. When we have the neutrons, they collide with this, they become slow, and hence with this particle, they collide. Understood?
Yes, ma'am.
Now let's have a look at the critical mass. What is critical mass? So another very important factor, that is critical mass. It determines whether the chain reaction can take place in the size of the piece of the uranium or not. Suppose if it is very small, then before the neutron had traveled a very far enough distance, it will be slowed down. So then they will have to left the reacting piece of the uranium. Okay.
Yes, ma'am.
Okay. The minimum mass required for the chain reaction is known as critical mass. Understood? We collide the neutrons with the other atoms to slow them down and also to increase their or change their masses as per the nuclear fission reaction, Akshita. Okay. So we make them that much of the mass that they should collide with the uranium atom. So the the minimum mass required for a chain reaction is called critical mass. Done?
Yes,
Fine.
ma'am.
So this is it for the day, Akshita. Okay, let's continue tomorrow.
Yes, ma'am.
Only one topic is remaining from this chapter, and that will be your nuclear reactor power station. I will explain that power station and we will go for E5 chapter. Done?
Okay, ma'am.
Okay, bye.
Bye, ma'am. Thank you.